We are Chemical Engineering Group 2, and our project is titled Computational Fluid Dynamics Analysis and Symbolic Regression of a Water-Oxygen Separator in the Hydrogen Production Process. Fossil fuels are quickly depleting from the Earth to be used as unclean energy sources. In 2019 alone, there were 36.7 billion metric tons of carbon dioxide fluxed into the atmosphere, contributing to a concentration of about 410 parts per million in the atmosphere. Nel Hydrogen wants to explore the usage of renewable energy sources, specifically hydrogen, as fuel. To produce hydrogen that can be used as fuel, we need to have several unit operations, including an electrolyzer and a water-oxygen separator. In our process, the electrolyzer's products of oxygen and residual water feed into the water-oxygen separator. This separator is important because if unwanted oxygen were to enter any downstream operations, this could result in pump cavitation. It is our task to improve upon the separation efficiency of this unit operation.
To design various vessels and find their relationship to separation efficiency, our team used computational softwares to simulate the separator and make a surrogate model. ANSYS Fluent was selected as the appropriate computational fluid dynamics software because it is capable of simulating multiphase fluid flow using different types of mathematical models, and it creates visual animations and representations of the separation process. The second software we are working with is ALAMO, which stands for Automatic Learning of Algebraic Models. It uses machine learning methods to create algebraic surrogate models between the inputs and outputs of a black box system. In our case, however, this is a glass box system, meaning we can see the behavior occurring in the system, but still need to figure out what's going on within it specifically. The glass box system our group is working with is the relationship between separator geometry and efficiency. We want to be able to manipulate design metrics to maximize separation efficiency. The way we plan to do this is with this workflow. First, we generate data from ANSYS simulations. Then, we find possible correlations via literature review that we could use as basis functions of the regression. A basis function is an equation involving the selected independent and dependent variables that ALAMO can use to expedite the regression of the inputs and outputs. After we have a surrogate model from ALAMO, we validate it by comparing the output of our model with the output of more ANSYS simulations. The metrics mentioned in the last slide are inlet velocity, tank height, tank length, and presence of baffles. These were selected as they were observed to have the most impact on separation efficiency. Our team defined efficiency by focusing on oxygen flow through the water outlet pipe, and is therefore defined as 1 minus the mass flow of oxygen from the bottom of the tank divided by the oxygen flowing into the tank. This equation is applied to each experiment, which is how we generate our dataset of efficiency values versus various design parameters. Ultimately, our goal is to find an equation that has efficiency as a function of all of these metrics so that Nel can use it in designing their separators.
Multiple simulations, including this one, were calculated to capture the data to obtain our model. The red represents oxygen and the blue represents water within this figure. A separator with high efficiency will ideally only have water or the blue fluid in the simulation exiting the bottom of the tank. After developing our surrogate model, the team was able to propose and validate a design with high separation efficiency. The pillar of environmental, ethical, and societal impacts of any process is the degree of sustainability of the process. Optimizing the separator will create a water recycle stream back into the upstream unit operations. This will maintain a sustainable hydrogen production process by eliminating water waste and letting oxygen out into the environment. Most importantly, high efficiency of the separation process will positively impact the production of hydrogen for renewable fuel applications. We would like to thank our faculty advisor, Dr. George Bolas, our sponsor, Andy Romer from Nel Hydrogen, our senior design instructors, and the Chemical Engineering Department for all of their support through this senior design project.